Real exam questions. This is question 69 about beam design and the serviceability limit state. Does a beam in serviceability limit state Q comply with the stresses and crack width requirements under a bending moment of 100 kilonewton meter, where the effect of the permanent load is equal to the effect of the mobile load? The environmental class is EE3 to the Belgium annex, or to the international code, it is XC4 and XF1, and the creep coefficient is 1. Concrete quality and the steel quality is given, and the concrete cover is 50 millimeters. The reinforcement is 3 diameters 20, and in compression 3 diameters 12, and the width is 300 millimeters, and the depth is 700 millimeters. The tensile reinforcement is 3 diameters 20, which gives you 942 square millimeters. The compressive reinforcement, 3 diameters 12, gives you 339 square millimeters. The maximum allowable concrete compressive strength in SLSQ is 0.45 times the characteristic value, and this comes to 11.25 megapascal. The maximum allowable stress in the reinforcement in SLSQ is equal to 0.8 times FYD, which gives you FIK, and which gives you 400 megapascal. The maximum crack width is 0.3 millimeter. The effective depth is then the total depth of the beam minus the concrete cover minus the stirrup and minus the point of gravity of the tensile reinforcement, and you have 632 millimeters. The point of gravity of the compression reinforcement, starting with the most compressed fiber on the top, it is the concrete cover, the diameter of the stirrups plus the point of gravity of the compressive reinforcement, so D2 is 64 millimeters. The K value is equal to the effect of the permanent loads divided by the effect of the mobile loads plus the effect of the permanent loads. Because in this beam, the permanent loads are equal to the mobile loads, so this factor K is 0.5. So we got that the K factor is 0.5 and the creep coefficient was 1. The mean modulus of elasticity is given by this formula with SCM, the mean value of the compressive concrete stress, is equal to 25 plus 8 divided by 10, and the mean value of the modulus of elasticity of concrete is then 31,500 megapascal. The modulus of elasticity of the concrete on the long term is the mean value divided by 1 plus K phi. K value, we know it's 0.5, phi was 1. So the modulus of elasticity of the concrete that we are going to take into account is 20,984 megapascal. That is the long-term value. Alpha on long term is then the modulus of elasticity of steel divided by the modulus of elasticity of concrete, and alpha is 9.5. Usually we expect a value of alpha around 15. So now we are careful, we find something which is much lower than 15. And then when we look at it, then we see immediately that this is because the creep factor is not very high. Normally the creep factor is 2 or 2.5. So in this case, the creep factor was small, so it's all right that we have a ratio alpha, which is on the low side. The concrete compressive depth is equal to the point of gravity of the fictive cross-section. The fictive cross-section is alpha times the reinforcement plus the concrete cross-section. You can work this out, and then you've got this concrete compressive depth. We fill in all the variables that we know up till now, and we end up with 161 millimeters. The concrete compressive stress on the top fiber is equal to sigma c, and is, of course, because it's elastic calculation, MSD divided by E over V of the fictive cross-section. V, of course, because you are working at the top fiber, V is, of course, equal to the depth of the neutral axis, which is x. The moment of inertia is then given by this formula, because it's the moment of inertia of the fictive cross-section. We can fill in all the different parameters, and we end up with this figure. Then the concrete compression stress, sigma c, was equal to this. We can now use the values of E and V. E is expressed in 10 to the power 6, which is much easier to handle. So we got the concrete compressive stress as 6.6 megapascal. The tensile stress of the reinforcement is then, of course, sigma S1 is alpha sigma C times this. And when you put in some numbers, we got 184 megapascal. And the compressive stress reinforcement of the compressive reinforcement, the stress of the compressive reinforcement, sigma S2 is then equal to this. We put in the numbers and we get 38 megapascal. So you see that the compression force is not very usefully used. The mean tensile stress of the concrete, the mean allowable tensile stress of the concrete is 0.3 FCK to the power 2/3, is 2.565 megapascal. And the cracking bending moment is MCR. So we have now checked the stresses, and now we will look, or calculated the stresses, now we will look at the calculation of the crack width. But first we must check that the applied bending moment is bigger than the crack width, otherwise you do not have crack widths and the procedure of calculating is wrong. So the concrete compression depth of the uncracked section, because we are not going to calculate the cracking bending moment. You start with the uncracked section. So that is the point of gravity of the fictive cross section where the section is not cracked. And then we can fill in some numbers, and XE is 357 millimeters. You see, this is larger than the one with a cracked section. The surface moment of inertia for the uncracked section is then equal to this, with the effective or the fictive cross section. Different values of the parameters are listed here. We first start with calculating the first part of the equation, which gives you this number. Then we add the second part of the equation where all elements are given, like alpha is 9.53, AS1 942, D is 632, XE is 357, and so on. So the EE value is then equal to 9,542 to the power 10 to the 6th millimeter to the power 4. The value of V, now must be careful, the value of V, it's the fiber on the bottom, but on the lower part of the beam. So V is not equal to X, but equals to H minus XE, which gives you 343 millimeters. The cracking bending moment is then the mean value of the tensile stress times E over V, gives you 71 kilonewton meter. So we see that this cracking bending moment is smaller than the acting bending moment, so that's okay. That means that the section is cracked. So we now go do a crack width calculation. We are calculating AC effective, and we take then the minimum value of those three, the minimum value of H over 2, or 2.5 times H minus D, or H minus X divided by 3. The minimum value is then 170. So AC effective is the width times AC effective of A is the width times HC effective, and gives you 51,000 square millimeters. The reinforcement ratio is then equals to the tensile reinforcement divided by the 51,000, gives you 0.01847. Crack width is a long-term calculation, so the factor KT is 0.4 for delta epsilon, which is the mean of the, which is the difference in strain of the mean value of the concrete of the steel strain minus the mean value of the concrete strain, is equal to this formula and must always be bigger than this value. So when we put in the corresponding values, then we see that delta epsilon is 5.9 10 to the power minus 4, and it must be bigger than this value, which is 5.52, so this is okay. So now we can calculate SR max, which is equal to this formula, with 0.8 is for bonding. So when you have steel with a good bonding, it's 0.8. Because it's about bending, this is 0.5. If you talk tension force only, then it's 1. This is a calibration factor times the diameter of the tensile reinforcement divided by the ratio of reinforcement. So then you got the maximum distance between different cracks, which gives you 354 millimeters. And the characteristic value of the crack width is then the multiplication of those two. And it gives you 0.21 millimeter. So the conclusion is the applied concrete compressive stress is 6.6 and is smaller than the allowable value. The stress in the tensile reinforcement is 184 and is smaller than 400, which is allowable. And the stress in the compression reinforcement is 38, which is also fine. And the crack width is 0.21 millimeter, where the maximum crack width is 0.3, so this is also fine. So the beam complies in serviceability limit state Q concerning the stresses and crack width.